Again, Abdullah Imran from Purdue University presenting SARA, a way for securing Android Remote Authorization. So before we talk about SARA, let's talk about what remote authorization is. It's a very commonplace thing that happens in today's mobile phones is when we use our mobile phones to authorize an action on a remote server. For example, you could use your mobile phone to trade stocks, or you could use your mobile phone in a bank app to transfer money to someone that you know. Now, due to the highly valuable nature of these authorizations, we have to make sure that these are secure against the most resourceful of attackers. Keeping that in mind, our attack model assumed that our attacker was able to compromise the OS, making sure that he was able to manipulate inputs and outputs as well as alter program flow. We also assumed that he has sporadic physical access, meaning that he could access the device at different times randomly for different intervals of times. So, next question is, can we use something like TrustZone or trusted execution environment to stop these kinds of attacker? The answer is yes, but it's not so easy. It's a very complicated way. Let's look at existing APIs in Android that leverage the TrustZone that help us protect against these threats. Firstly, we have key storage in TrustZone, which allow us to store cryptographic keys inside the secure TrustZone. Nextly, we have a key attestation, which allows a remote server to attest that the key that is being used to sign a particular is stored inside the cryptographically secure hardware. Thirdly, we have something called the TrustZone controlled secure UI. Now, this is a special screen that is controlled by the TrustZone, and it ensures that whatever is seen on the screen, like this prompt, is exactly what is signed. And in order to sign this, you have to press a specific button, like this power button on a Pixel 3, which you have to double press to confirm this. And this input goes directly to your secure hardware. Lastly, we have biometric prompt. This allows you to authenticate yourself biometrically using most commonly a fingerprint or even a face scan these days. One note about this is that even though your biometric input might be going directly to TrustZone, this prompt being shown is not controlled by the secure hardware. This is OS controlled only. So keeping in mind these particular APIs, we decided to investigate how apps in the market were using these. So we investigated over 100,000 apps from the Google Play Store from various fields, keeping in mind some filters like number of downloads. And then we looked into certain APIs. So for example, we found that none of these apps were using the Android Protected Confirmation app. And keep in mind, these apps were all financial, business, marketing-related apps. We also found that the key attestation API was only used by 5 particular apps. And even then, they were only being used for local cases, which is not the purpose of this particular API. It's supposed to be used remotely to send attestation data to remote servers. So why did we get such results? Why did we get no apps using these? So our initial hypothesis was, it's because, well, they're really hard to use. And that would make sense considering the complicated documentation that comes along with these particular APIs. We also looked into these APIs themselves and found that they had certain limitations that we needed to deal with. For example, the biometric prompt has the fake prompt issue, in which case this is the prompt that is shown to the user, but since this is not controlled by the secure hardware, an attacker could potentially show that prompt to the user, but in the background, he would be signing something like this. And therefore, even the user might think that he's sending something to Alice. He might end up sending it to, well, himself or someone else. Or he could even change the amount if he wished so. And the user would know the difference. The second form of limitations that we found were with the Android Protected Confirmation API. And for that, it's a very simple limitation. Firstly, if you think about the legitimate user, is that you only have to press a hardware button. It does not take any form of authentication to press that button, which means that anyone who is able to access your phone for even a second is able to double press that hardware button and move along, therefore authorizing that action on a remote server. Therefore, using any of these APIs alone or using them together in a cryptographically insecure way will lead to vulnerabilities. Therefore, keeping all of those things in mind, we developed our goals. Firstly, we have usability goals. First thing we wanted to do was to make them easy to use for developers. Keeping in mind our market analysis, we think this was really important. Seeing that no one in the market was currently using them, we wanted to provide the developers with an easy way to leverage these APIs. Secondly, we wanted to use existing APIs only. The reasoning behind this is that we've seen in past papers the solutions leveraging TrustZone aren't implemented in the industry because they require making changes to the hardware or to the TrustZone itself, which require vendor collaboration, which is pretty hard these days. So that was our reasoning for our second usability goal. Now, for our security goals, we wanted to make sure to protect against OS compromise, we were making use of the T, and we were making use of key attestation. We also wanted to make sure that the user was aware at all times of the transaction or authorization that was taking place. And we also wanted to make sure that the server was able to fully verify that this entire signing procedure was taking place inside TrustZone. To prevent against physical attacks, we also have to make sure that we physically authenticate / authorize users while the user is aware of the prompt. Keeping in mind these goals, we came up with SARA, where we leveraged the following Android APIs to come up with our own authorization protocol we call biometric confirmation, and we packaged them into a server module and an Android library that we open sourced. So here's the SARA's process from the user's perspective. Firstly, you have to enable the process itself. This is a one-time only process which allows you to generate the key pair and initiate the attestation on the server side. This is usually done from your settings menu from the particular app that you are deploying this in. For every action that you need to authorize, the first thing that the user will see is a biometric prompt that will look like this. He will have to provide his biometric input, usually a fingerprint or even a face scan if your device has it. Then in the background, the prompt gets signed using the valid biometric input, and then the user gets to see this particular confirmation prompt. Notice how these two prompts have to be matching for this signing to take place, or otherwise the server will not verify this signature. Next, once the user sees this prompt, he has to double press that power button, and then that's how the second signature takes place in the background, and that is sent to the server for verification. On the developer side, we have a really simple package. On both Android side and on the server side, you just have to import our library, call one function or two functions for setting up the protocol, and then one function each to authorize the action. And that's it. Everything else is taken care of by SARA. And the reasoning behind this is because this is a very complicated cryptographic process, and we believe developers, your average developer is not associated that well with cryptographic functions. Therefore, we wanted to take care of that for him in the background. Second thing, the reason why we came up with the server module is because since this is a remote authorization procedure, a lot of things have to be checked on the server side. And potential vulnerabilities could occur on the server side if checks were not completed properly. Therefore, we also make sure that we also provide a server module which does these checks for the developer. In order to evaluate SARA security, we came up with a ProVerif model. ProVerif is a cryptographic protocol verifier, and we used it to model processes such as the user, the client, and even the adversary or the accomplice, as we call it, which acts as the person who might press that hardware button on your phone. And we use this ProVerif model to verify that our security goals, that the legitimate user is able to see the action he performs on a prompt, is able to physically authorize it, the action that he's performing, and then the server is able to have a guarantee that the legitimate user is the one who has authorized the action. Furthermore, we also used our ProVerif model to show that there were possible attacks if the APIs were not used in a cryptographically secure manner due to the limitations as we discussed before. To evaluate the usability, we came up with a user study where we compared the native API and SARA's API. To do that, we divided it into two identical tasks containing C subtasks each, and we wanted to answer two questions. Does using SARA make it easier for developers to use Android's T-enforced APIs? And second, how long does it take for a developer to learn how to use SARA? To do this effectively, we had to recruit participants who were familiar with Android. Therefore, we had a pre-screening questionnaire in order to filter out participants based on their expertise level. These were the results of completion. We had 3 subtasks. In the first subtask, they had to create the key pairs or key pair, depending on their preference, In the second subtask, they had to show the prompts and have the user sign them. And thirdly, they have to deal with the server-side attestation. As you can see, the results were pretty one-sided. Then we also had an evaluation survey at the end. The evaluation survey also had questions from the system usability scale, and we got, for SARA, we got a score of 95.18, whereas for the native API, the score was only 11.61. As a reference, an average score of 68 is considered good, whereas 11 is pretty low on the scale. Keeping that in mind, I think we were able to verify our hypothesis that the native API is indeed very hard to use, whereas SARA takes care of all of those complexities and makes it easier for the developer to use. So in conclusion, we made SARA easy to use, and we made sure that it uses existing APIs so we can use it on all existing Android devices. And we also made sure that it provides root resiliency in case of OS compromise. We made sure that it even had some sort of resiliency against physical attacks, where the accomplice was present and had access to the phone in a sporadic manner. We also evaluated SARA security using ProVerif. And lastly, we did a user study to ensure that we evaluated its usability. With that, the floor is open to questions. Our code is available online on GitHub, in case anyone wants to use it or look at it. And that's it. Thank you.